Hello everyone, it's Benny, and welcome back to the 3D game programming tutorial. Today, we're having a special bonus video, and this is a true bonus. There is nothing in here that's essential to follow the series. You can skip this and be totally fine if you want to. But what we're going to be doing in this video is we're going to be taking a look at how we can push our crazy number of objects even further. We're going to profile our engine as is, see what's taking time, see what isn't, and see if we can do any better than the object count we have without going completely insane. Because odds are there's a few things we could do to speed it up. So this is for people who are interested in optimization, interested in what it takes to push their game to a limit. Granted, your game's probably not going to be limited by having stupidly huge numbers of objects on screen at once, but the idea is this will give you a general feel for what it's like to really optimize a game, where your pressure points are maybe not likely to be, but how you can hunt them down and address them effectively, because optimization is infamously counterintuitive. So yeah, we're going to take a look at that for those interested. If you're interested, come join me. We're going to have a fantastic and interesting time. And if you're not, that's fine. I will see you in the next video. So let's begin. So I have disabled VSync again. I have set should render to true, meaning we no longer have a frame limit on our game. And I have built the release version of the executable. It's important to have the release version or you're basically going to be meaningless. You're going to be profiling the debug build, and that's not going to work very well. So, once you have all that, we're going to go to build, and we're going to run CGFX5, our executable, through a profiler. This is very platform dependent. Profilers are not very well standardized, and they're often hard to get your hands on a decent one. If you're on Linux, a good one to use is Valgrind's callgrind tool. So Valgrind tool equals callgrind, and we'll just say /CGFX5. If you don't have a good profiler, that's fine. You can just watch my videos to see what the results are. Oh, do I have to put it in quotes? Do I have to put like dashes? Okay. Oh, and I misspelled it, okay. Never mind, I was mildly confused, but everything seems to be working out now. Alright! So yeah, we're just gonna run, and you notice it's running way slower than usual. And that's why I have my number of objects decreased to about 5,000. So, much lower, and even that much, you can see, already not even hitting 60 frames per second anymore. But other than that, we can still run the game. But yeah, the reason is, for Valgrind's profiler, it actually does a little bit of emulation. Specifically, it emulates the cache, I believe, if I'm not entirely mistaken. And because it's emulating something, that just adds a whole bunch of overhead. So, there you go. But the good news is, we now have our output. We have profiled. And now we can open with KCacheGrind. It's a program for Linux. There may be one for other platforms if you're somehow using the same profiler. And yeah, I'm just going to open this up in a new window. And we get this nice breakdown of where all the time is going in our program. So basically, the bigger the square is, the more time it is taking up relative to our program. But really, you can just look here too to get the same general picture. So the most time is being spent between, if I scroll over, between the update system of multiple components and the update components in the mesh render system. And you notice that these are the methods actually taking the time because this is the self time. This is the time in the method itself, and this is the time in that method and all subcalls of the method. So we're spending a lot of time with updating components and a lot of time in the renderable mesh system, which is actually interesting. I'm not entirely sure I understand why the renderable mesh system of all things is taking up so much time. I will have to definitely look into that. Forced Ruth, of course, takes up a little bit of time, but that's to be expected. We are using a somewhat fancy integrator, but it's not like that insane. It's like 3 times the cost of a traditional Verlet integrator, which is pretty darn fast, so yeah. And these are the big costs of the program. Everything else, essentially nothing. Alright, so we have our profiling results, and there's a few things we can take away from this. First of all, our performance burden is relatively balanced. It's split between the rendering, the ECS overhead, and the movement. So there's no one giant bottleneck. We're pretty evenly hitting a couple of things, give or take. We're not hitting the motion quite as much as the other two, but still. So even if I made one of those instant, we can expect at most a 50% speed up, which is nothing, but you get the idea. There isn't a single hot zone. But that doesn't mean we can't do anything, because all these hot zones really have one thing in common, and that is data. None of these are doing anything super computationally intensive, so it's almost certain that the bottleneck in all of them is the amount of data. So what we can do is we can reduce the amount of data we're sending somehow without too much of an increase in computation, and that should give us a little bit more performance out of everything. That's sort of the general reasoning you have to go about this with. So, right now, another thing we could avoid is the overhead of update system with multiple components altogether. Like I said, this isn't going to be a huge win for us, because this is only so much of an issue, right? But here's the thing, if everything is in a single component, that doesn't even get called. Everything is updated right here in this much simpler loop, so that would avoid whatever performance issue we may be running into here, which, frankly, probably the memory. But that's fine. So that's what we're going to do. We're going to try to create a new component that, sort of a mega component that takes in everything, and we're going to see what we can do with that. So let's make our mega component. I'm going to go down here. I'm going to call it struct mega cube component. Sure. Doesn't really matter. So our mega cube component. How can we make this any smaller than it is? Well, first of all, for starters, we don't need a full transform. We don't care about rotation and scale. For what we're doing, we only care about position. Now, so I'm going to create a position, and I'm going to specify it as a float array of 3. Because our vector does use an extra float slot as really just to make it easier to use with Simd, really. So this will reduce the memory a little bit. Will it make a difference? Maybe. We'll see. So, same sort of concept here. Position, velocity, and acceleration in our megacube component. So that's pretty much everything we need. That's equivalent to the transform. This is the equivalent of the motion component. The only other thing we need is the renderable mesh. Here's the thing. All of them have the same vertex array. So we don't need that. That can be stored in the system itself. And the texture, there's only 2 options. So what I can do is I can have a uint8 text index, which I'll just default to 0. I don't need to default to anything. But yeah, this will be either 0 or 1 depending on which texture we want to use. So we can have like an array of different textures to use, and this text index will select which of those textures we are using. Pretty straightforward. And yeah, this is how we're going to set up our mega cube component. Now, on the systems side of things, for our mega cube component, we need something very similar to the motion system. So I'm going to take a mega cube motion system, because we need to move. That's the big thing it needs to do. Of course, it's only going to take in a mega cube component, and that's going to be the only one of our base components. The mega cube component, I'll just call it comp, because it's our only component. So essentially we want to do something very similar to this, except, well, with our position velocity, with these. So what we're going to do is we're going to convert. So we're going to set a new position is a vector 3f of comp position 0, comp position 1, and comp position 2. There you go. That is our idea. And same thing for our new velocity, because we want the same sort of thing. And acceleration is constant, so I'll just do that. So other than that, I'm just going to copy and replace. That is the policy here. Copy and replace. There you go. And once we have these as vectors, we can pretty much just do the same thing we did. So new pos stays the same. We need new velocity as a parameter. And we'll pass in acceleration. Boom, motion integrator does its magic. We have the new position, velocity, and everything. So now we just need to set our, well, yeah, our position to our new pos sub 0, and same sort of concept. 1, 2, 1, 2. Alternatively, you could do this in a for loop, but I'm doing it this way just because I already started on it. So yeah, and it doesn't matter too much anyways, so I am not too worried about it. We also need to move over to the velocity this time. And the reason we need to be careful about the velocity is because these integrators do change the velocity. Over here, it used to be implicit because it was just modifying the motion component. Now we're not magically modifying that anymore, so we have to be careful. And acceleration is constant, so we're okay. We have mega cube motion, just like that. So we can move it around. All we have left now is rendering. So we're going to do something, again, very similar to our renderable mesh system, but this is going to be our mega cube renderer. There you go. So for our mega cube renderer, we are going to take in the game context just like before, but we also need now a vertex array reference called vertex array, and we also need a texture double pointer called textures, and a size t for num textures. Technically, we don't need num textures. We're just assuming it's big enough. So technically, we don't need that, but it's good practice to have it. So we're going to have it anyways. So I'm going to now introduce myself to the bizarre tab issue. So yeah, vertex array is going to be equal to vertex array n, which we don't have yet, but that's fine. We'll have it soon enough. Texture will be textures n, and num textures, guess what? It'll be num textures n. There you go. So for our actual method, pretty straightforward. What we can do is change this to a vertex array. And I almost forgot our component type, of course. What on earth did I just do? Okay, never mind. So mega cube component. There you go. That's the only component we're dealing with. So I can just say this is the only pointer. This is comp. There you go. So that we also need textures. And we're going to ultimately dereference this because it will give us a pointer, but that's fine. Because what I'm going to do is going to use that index, text index is what I called it. There you go. And yeah, we're just going to use it. So comp.text index. There you go. And last, we need a transform. So transform. And actually, I'm pretty sure we even have a constructor that's genuinely just a vector 3f of, in fact, I can even scroll up a bit and copy and paste this from, yeah, our new pos. Pretty confident I have a constructor for it that's like that. So, make a cube renderer. There we are. So yeah, vector 3f of all this. We have a transform. And just like that, we now have our mega cube renderer, except I forgot the parameters in the constructor. So let's just go ahead and add that. Very simple though. We need a vertex array reference, vertex array n. We need a texture double pointer, textures n. And we need a size t, num textures n. There you go. It has been handled. So with that, all we have to do is to use this magical mega cube component instead, and we should be okay. So I'm going to create a mega cube component, mega cube comp, sure. It's as good a name as any. and I've commented out make ECS entity because we're going to do it a little bit differently now. Now I am going to use a for loop trick, so I is less than 3, I++. And what I'm going to do is say megacubecomp.position sub I. That's going to be equal to transform component dot transform dot get translation sub I. So I'm going to reuse my old method of initialization here. So my velocity, motion component dot velocity, and this particular index. And lastly, acceleration, motion component dot acceleration. There you go. And the only thing left is we do need the texture. So rather than copy that, I'm just going to do it again. So megacubecomp dot text index equals if it's more than 0.5, it's 0. Otherwise, it's 1. So there. Sorry. Otherwise, colon, it's 1. There we go. That should initialize our megacube component. Now we should be able to do ECS.makeEntity megacubecomp. There we go. That should handle a lot of the issues we were having. We do need a couple more components though. We need our megacube motion systems. Which actually, is that even what I called it? Is that I called it megacube motion system. Good. What a name. I'm just going to copy and paste this because I really don't feel like typing that out again. And we need our megacube renderer. Which takes in a ridiculous number of parameters. Namely, it needs a game context. It needs our vertex array. It needs a list of textures. So I'm going to say texture pointer textures equals, and it's going to be an array equal to texture 2. Is that what I called it? I feel like I had a name for the other texture. Bricks2 texture. There we go. Just the address of these two textures. So the address of texture and the address of Bricks2 texture. There we go. We have an array of the pointers we need. We can pass that in. And I believe I have a macro, array size in elements textures. We're done. Almost. Actually, I forgot to actually add them to the system, so yeah, under our main things, we will add a megacube motion system. Under our renderer pipeline, we will add a megacube renderer to our rendering pipeline. And this should be doing everything as a single monolithic component now. Alright, and we have a few errors, namely because I forgot to cast these components to megacube components in both the motion system and the renderer. So you can't fault me for inconsistency. That's renderable mesh. There you go. Megacube renderer. And that should fix the errors, I think. Megacube.text index. Okay, no, it does not. 224. Because I forgot to do it with arrow notation. Okay. And transform.toMatrix by itself, because transform is a local variable. And there you, oh, hello. I accidentally did these with monkey heads. Oops. Well, we know it's working. You know, that's a step in the right direction. But yeah, we want the tiny cube array. Wherever you are. Tiny cube array. There you go. So 5,000 tiny cubes. Hey! And it explodes, and it's going very, very fast. We're spending about a quarter of a millisecond for 5,000 cubes. Let's try up in it a bit. Let's try our 100,000. So it's 10,000. Let's try our 100,000. This used to be 10 milliseconds, and now, with our reduced memory usage, it's still 10 milliseconds. That is unusual. That is not what happened during my initial tests. One moment. Okay, so as it turns out, my screen recorder is interfering with the test a little bit. It's causing just that touch of extra overhead that's screwing with the whole thing. If you turn the screen recorder off, the results are as expected. So, there you go. I don't know what to tell you. The results are there, even if I can't show you to them in the video. But yeah, point being, if you do the testing, I found that somewhere around 160,000 gets about the same performance as the original 100,000 with this scheme, which is about what I expected. What's interesting though is in my initial test project, it actually runs faster for no apparent reason. If I just go ahead and show you, this is my initial project that I built just as proof of concept. Oh. Well, never mind. Apparently it is victim to the screen recorder overhead as well. Never mind then. Now we know. Screen recorder is the X factor that's screwing everything over. But yeah, things are reasonably faster now. If I look at our profiler, you see ECS update systems alone has gone down a bunch. And stress test of update components has gone up. The motion system update components has gone up a little bit by itself. Probably because of all the overhead of creating the vectors and whatnot. But here's something you got to keep in mind at this point. All these things these methods are doing are very, very dead simple. These are not complicated methods. We are not doing advanced calculations. This is pretty dead simple stuff here. So, really, we're not terribly far off from what the system can do under this configuration. That's not to say it's impossible to make it any faster. You can definitely do it faster, but you're going to have to get increasingly creative with how you organize your data and how you update it, and you're going to get increasingly diminishing returns by doing so. So, the big takeaway from this video is, if you're clever about what you do with your data, if you're clever about how you use your components, you can make things run faster than otherwise. As we saw here, we got about 60% faster just from that simple arrangement. So there is stuff you can do to speed everything up. But as always, don't expect miracles. Cleverness can get you better. It can't fundamentally make a slow process not slow. So bear that in mind. This might be able to tip you over the edge, depending on what you're doing. It's probably not going to save you if you're doing something horrible or stupid. But it's good to know. We can have a stupidly large number of objects on our screen if we want to, and it is fantastic. So, that will be all for this video. Thank you for joining me on this little bonus excursion. I hope you enjoyed, I hope you learned, and I will see you all in the next video. Thank you very much for joining me. As always, if you want to talk more with me or other like-minded people, you can join the Benny Discord. And if you want to find out what happens next in the series right now, you can do so by becoming a Patreon supporter. And a special thank you to all my patrons for making this video and all my videos possible. Thank you very much. I will see you all next time.